I did in the first lecture. So, we started with the notion of an event, which now with the sophistication of 4 vectors we will denote it as xi, which stands for t and let us say xyz, even though this could have been traded off for some r theta phi or something. More generally it is like t, a zeroth component and a 3 vector x here. Okay. This is what we started with as a fundamental entity. Then we found that there exists a set of transformations which we call the Lorentz transformations, which when you go from one prime to another transforms xi to xi bar or xi prime, which is some linear transformation with L I prime j xj. More precisely, I told you that it is better to think in terms of differentials dxi and dxj and say that they transform like this. Okay, this we have already done, and we also have the explicit form of the expression, which was like x0 prime is gamma into x0 minus v, let us say x1, and x1 prime equals gamma into x1 minus v x0. There I gave you an exercise to work this out from light clocks. I am sure you would have done that. So,
there is a question in that exercise to determine the two functions.
Yes.
So I do that. So I get an equation, and I get an equation in.
You have to solve that simultaneously. F0 and F1 is easy to obtain, because one of them is t over gamma t and the other is gamma vt, right? And then you had one equation which said t prime is equal to some half of t minus t naught and x prime is equal to this, which you can solve back for getting.
I cannot use simultaneous because the functions are at different times tau 1 and tau 2.
No, you just need to do this a little cleverly. Okay, give it a shot. It is going to go into the assignment set anyway, and if we don't get it, we will have a tutorial session.
Observation, because I can see that equation I have.
No, actually, there is a constructive way of doing it. It will actually flow through. I mean, it is. There is just one place where you have to be a little bit careful. Rest of it is trivial. Yeah, right. Okay. So you will get something like this, and then I said that any quantity, any 4 quantities, which I think I denoted as qi. Let me just close this door. Yeah, any quantity is qi which behaves like qi prime equals the same L I prime j qj is defined by definition. This is a 4 vector. Okay. Along the way, we also introduced, given this xi's, the line interval ds square, which we wrote as eta ab dxa dxb, and worked out its properties. In particular, we knew that the ds essentially refers to the proper time of a clock as it moves along a trajectory. So, this is just to summarize what we did, and now we will proceed further with that. Now, there are 2 or 3 ways in which you can go from here. First is a completely physics based approach, where we start with this and we define sensible 4 vectors. I already defined 4 velocity in the last lecture, and we can go further and define more quantities along those lines, work out their properties, develop the dynamics of a particle introducing an action principle, etc., which I will do. The other thing is to develop a little bit of formal mathematical machinery dealing with these 4 vectors and their associated quantities, which are like 4 tensors, etc. I would prefer to get that out of the way. So, it might look a little mathematical for the moment, but we will very quickly connect it up. Okay? So, I will just do that, and then we will go back to the physics. So, let us look at this qi which is written down here. To begin with, you should be able to immediately get from that the translation, that if I go from one prime to another, q0 bar prime should be gamma into q0 minus v q1. This is exactly analogous with the previous one, and similarly the other equation for q1. Okay. So, this is the definition of the 4 vector which we have introduced. I want to have at this stage another quantity which is very similar to this, but with indices at the lower end. This I introduced briefly in the last lecture by saying that if I have a qi, I can define another quantity which I will call qj by eta ji qi. Just to remind you, for those who are not familiar with this, this is the lowering of the index and the I is summed over. Okay. So, this is definition. Then given this definition, you can define the norm of the vector as either qi qi, or which is the same thing, eta ij qi qj. Okay. And because we know the structure of eta ij, this is also equal to q naught the whole square minus the spatial part q modulus square, right. So, last lecture in the end when I asked whether I should go faster or slower, there was this comment that definitely not faster, but if it has to be slower, you should just slow me down. I mean, you should just say that stop there and go over that again. Okay. So, I am assuming that you guys have done a sensible tensor analysis course, though it may not be in the context of special relativity. Okay. So, this is the norm for a vector, and given any 4 vector you can define that, and this from this we know that this is just the norm of dxi, and just as this is invariant, by explicit working out you can show that this quantity is invariant. So, it has the same value at any inertial frame. Now, suppose you have two different 4 vectors. Let me call them ai and let us say bj. What all can you do with them? The first thing you can do is you can take these two and multiply and obtain from them an object which I will call mij, which is by definition ai bj. Now, ai has 4 components, bj has 4 components, so mij in general has 16 components, 4 by 16 independent components. Okay. This is a very special kind of an object. If you think of it as a matrix, not every matrix can be written as a product of 2 row vectors. Okay. So, in that sense it is a very special kind of a matrix, but nevertheless it is a matrix. We can now ask, if I go from one prime to another, how does this mij transform? That is very easy, because we know how aa and bj transform. So, we can immediately write down that m I prime j prime is equal to L I prime, let us say a, L j prime b MAB, correct. So, this is just substituting for each one of them, one factor comes from this, other factor comes from this. Of course, in this I never had to write a and b, therefore, I can now take this, and this is the way the mathematics works, you keep abstracting away the essence, you take this and you can define quantities with 2 indices attached to them, which under a Lorentz transformation transform like this and call them 2 tensors. Okay. So, this is a second rank tensor, and the definition of a second rank tensor is that when I go to another Lorentz prime, it has to transform in this form. Now, the rule is very clear, for every index you attach an L factor and it will take care of itself. And as we discussed in the previous lecture, you can't take 1 upon kx, 1 upon ky, 1 upon kz and then call it a vector. it has to transform in a particular way, that has to be independently verified by some physical considerations, and once that is done, then this is what defines for you the 2 tensor. There are a couple of results about this which again you would have done in tensor analysis, which I want to get out of the way. If you have a tensor with 2 indices, suppose you have something which is Mij, there is an issue, A and B, sorry, bad handwriting. So if you take Mij or any 2 indices of a multi-index object. Now obviously just as I can multiply like this, if I have another vector Ck, I could have defined a 3 index object as Ai, Bj, Ck, then the transformation will have that many Lorentz factors. So the generalization is obvious, I mean you can have a nth rank tensor with all indices on top by this rule. Now if you have any 2 indices, I am only writing 2 indices, but there could be some 13 more indices here, that we do not care. On any 2 indices, you can express this as a sum of a symmetric and antisymmetric part. So you can write this always as half Mij plus Mji exactly, then you have to add to it half Mij minus Mji, right, because this half Mji and half Mji will cancel out, half and half will give you 1, this is an identity, but it is a useful identity because this part is symmetric. When I change I and j, it does not change, this part is antisymmetric. So in general any Mij can be written as a part Sij which is symmetric in I and j plus another part Aij which is antisymmetric in I and j. So this can always be done. Yeah. L, okay, yeah, okay. This L is a matrix, this Lij is a matrix which originated from this line, which in turn originated from Lorentz transformation. Okay. So if you want it to be done explicitly, what you can do is let us write x0 prime, x1 prime, x2 prime, x3 prime as a row vector, and you think of it as multiplying L times another vector. A slightly better way of doing it, now that we are working with tensors, is just to expand out one of them and do the same thing, that is you take x0 prime and you write it the way I have written as L0 prime k xk. This is just this equation without d, okay. Then expand this out, so you will get L0 prime 0 x0 plus L0 prime 1 x1, and let us do in 2 dimensions, so there is nothing else. But we know that x0 prime from this equation, where is it, this equation is gamma times x0 and minus gamma v times x1. So this is gamma and this is gamma v with a minus sign, right. So I have given you 2 components of that. Similarly you can work out all the components. So it is just a matrix which tells you how this 4 vector is transforming. Is that clear? Okay. So you can write any tensor as a sum of the symmetric and antisymmetric part, and one result which we will keep using from now till eternity in our course is that if you have a contraction, by which I mean if I take a vector Aij which is antisymmetric and I multiply by another vector Sij and I sum over them, it is 0. Okay, I am assuming you people know the proof for this, I mean that is a standard thing. A corollary to this is if I take an arbitrary tensor here and hit it with this Sij, only the symmetric part of that will contribute, and vice versa. If I take an arbitrary tensor and multiply it with an antisymmetric tensor, only the antisymmetric part will contribute. For example, if eta ab has been an asymmetric tensor, only the symmetric part of that is relevant for this expression. Okay. So this is one case because this part is explicitly symmetric, that is an example of this. Okay. Fine. So, as far as the object which has indices coming on top is concerned, this is what it is. We will do this more rigorously at some stage, and the things with indices on top are what are genuine vectors and tensors. Things like this Qj with a lower index, in conventional textbooks including Landau and Lifshitz, which you will be reading, or my textbook, they make a distinction between what is known as contravariant vector and covariant vector. These are called, the ones which has the index on top are called contravariant vectors, and similarly contravariant tensors. Those which has indices at the bottom are called covariant vectors and covariant tensors. It works perfectly fine, you can do everything with that terminology, nothing will go wrong, but a differential geometer will have a fit. They do not think of these as vectors at all, they think of them as what is known as one forms and two forms, and I will describe what they are in a minute. I mean, not in a minute, probably in a couple of lectures down the line. I mean, it will take care of itself. So, do not worry about it. For the moment, we will just think of it as contravariant components of a vector and covariant components of the vector.
Why is that terminology, contravariant and covariant? What is the relevance?
Nothing, actually nothing, because contravariant and covariant was originally used in elasticity for a different purpose, and then this term came up. It is a very bad term because covariant is misused, because you say some equation is covariant, some expression is covariant, which has absolutely nothing to do with something being covariant. Okay, so it is a very bad misnomer, and anyway mathematicians do not care for that. They think of this as one forms and vectors, that is the precise notion, and because that structure is so beautiful, I want to spend some time developing it, and it is also useful in GR. So, for the moment you just use this as the definition. Okay. But I want to give you an example before, I do not want to sort of leave you dry there, because for 4 vector we have this beautiful example of dxj. You just take the coordinate differential, these are 4 vectors, and then you can divide by ds, for example, then the 4 velocity is a 4 vector, etc. What is the corresponding example for the lower one? Okay. Now, it is almost easy to guess. The point is, if you think dxi is going to give you a 4 vector on top, I mean the most obvious things which can give you a lower end is d by dxi, so to speak, right. This is the inverse of that. This is dxi is a differential, this is just the dxi put on the bottom, it is like a partial derivative operator. So, you look at an object like, take some scalar quantity phi. What do I mean by a scalar quantity? A quantity phi is a scalar if phi prime at x prime is same as phi at x. Okay. What it means is, a simple example could be the norm of some quantity, okay, that is definitely a scalar. So, at a given point it has a value, when you make your Lorentz transformation its value does not change. If you are thinking of 3-dimensional rotations, temperature is a scalar quantity. There is a temperature at a given point, if you rotate your coordinate system it does not change, it has a numerical value. The coordinate labels you give to that point will change. Originally you called it 1, 2, minus 5, after rotating you may call it 3, 4, 18. But the phi at that 3, 4, 18 would be equal to the phi at 1, 2, minus 3 with the numerical values being the same. That is a scalar quantity. Now you look at d phi by dxi, okay, and you can ask how that is going to transform under Lorentz transformation. That is again very easy, because I want to know what is this quantity, phi prime by x prime, but I already know that phi prime is same as phi. So, what I can do is to say d phi by dxj into dxj by dxi prime, right. Now, dxj by dxi prime is another matrix. So, I will write this as L, I will use the same symbol for the moment, L I prime j d phi by dxj. Now, how do I get this matrix? Okay. Here I want to treat xj's as functions of xi prime. Here we have treated x prime as a function of x, but we know that that only changes flip the velocity, because it is just the other direction of velocity. So, you can get exactly the same thing. all the v's has to be changed into minus v. So, you take this matrix, change all the v to minus v and then shift the prime from top to bottom and you will get this. So, this is actually the inverse matrix of this, and that is obvious by where I put the prime. In principle, you could have called it some other matrix. I mean, a purist would have denoted it with a L bar or K or something, but we know what we are talking about, so I have not bothered to do that. So, these quantities also transform under Lorentz transformation in a very particular way. Okay. Now, what could be an example of a object like this? There is a very sensible example. This is what is given by the normal to a surface and we will need this. So, let me develop that first. Suppose you have a surface, let us first do 3D. This is x, y, z and I have some surface in this, and at some point I want to define a normal to this surface. Okay. How do I do that? First I need to know what do I mean by this surface. A surface is actually given by saying there is some function s of xi which is constant. If xi goes x1, x2, x3, I goes 1, 2, 3, it is a 3 dimensional space. I have said some function is constant, that gives me a 2 dimensional surface. No, right now I am talking elementary things like just 3 dimensional space. So, this could be like x square plus y square plus z square equal 3. So, it is a surface of a sphere of radius root 3, right. So, I am saying if you take a function and put it equal to constant, and in the same sort of way in 4 dimension I can take this xi where 0, 1, 2, 3 can come up, and there I have to ensure what you have said is correct, that this s transforms as a scalar. Okay, that function is given for you and by definition is a scalar, and that defines the surface for you. Now, a normal to this surface, a normal vector ni is very naturally comes with a lower index. It is defined as ds by dxi. How do I know that? Well, to do that, construct the following quantity. Look at ni dxi, which is by definition ds by dxi dxi, and remember that there is a summation over I. So, what does this mean? This means you differentiate s with respect to every one of the independent variables, multiply by that differential and add them up. So, ds by dx1 into dx1, ds by dx2 into dx2, dx2, but that is nothing but ds, just from your standard thermodynamics for example, is ds. So, if I take a direction dxi and I look at ni dxi, it tells you how much s changes along that direction. Now, suppose I take dxi on this surface, suppose this is dxi, I take it on the surface tangential to the surface, then I know that the s does not change on that surface because s is a constant, this will be 0. This immediately tells you that dxi which are tangential to the surface are orthogonal to this ni. Think of 3D for the moment. So, in 3D the dot product between this and this vanishes. Therefore, if these things are dxi's are tangential, ni is a normal. Okay. You just carry it forward to the 4 dimension. In the 4 dimension, that last bit about orthogonality you have to be extremely careful because of that minus sign. If you are in an Euclidean space, any dimension, this works. Now, why do I have to be careful there? Well, I have to be careful because in 4 dimension I can have vectors whose dot product with respect to each other can be 0 without they really being orthogonal in any sensible way. Okay. For example, you can have a vector qi such that this quantity actually vanishes. Okay, q square is always equal to that. I mean, then you have a vector like that. In fact, the momentum of a photon will be such a vector. Therefore, qi is 0. So, by this definition you should say that q is perpendicular to itself, while almost intuitively q is parallel to itself. So, the notion of parallel and perpendicular is slightly vague. Therefore, you use a mathematical apparatus and you say that this is the definition of a normal to the surface, whether it is Euclidean or Riemannian. Well, that is again a bit of a jargon. If the signature is all positive, you call it a Euclidean space. If some of the signatures can be negative, you call it Riemannian space. So, the space time actually has a Riemannian signature. This one comes with this plus, minus, 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 that is called the signature of the space, and here it can have negative and positive signs, that is called a Riemannian space. If they are all of the same sign, then you call it a Euclidean space. Okay. So, this is a good why it comes with a lower this thing. That is because I have already told you that d by dxj transforms like a covariant vector. Okay. So, what I did here was to give you an example where you have this d by dxi coming up. Okay. Now, once you have these two, you can do several beautiful things. So, I just want to illustrate to you one of them, I mean just to give you a power of that. This has to do with an equation, like if you take a vector, I told you that if in normal 3-dimensional vector calculus, if I have two vectors A and B and the operator del, you can do all kinds of things. For example, using del you can take a gradient, you can construct quantities like divergence of A, you can construct quantities like A dot B, you can also construct quantities like A cross B, and you can construct quantities like curl of A, right. This is all possible in 3 dimension. So, we want to know how to generalize these notions in 4 dimension. Okay. First of all, the gradient operator acting on a scalar function, gradient of some phi, del phi, that is already there. This is nothing but a del phi, right. So, originally your gradient was defined in 3D. So, your del phi would have been d phi by dx, d phi by dy, d phi by dz. Now, your gradient becomes d phi by dxi, it just adds here an extra d phi by dt, and then you take your normal del phi. Is that clear? So, the gradient operation is trivial, you just take all the derivatives, and in fact, most of the time we will simplify the notation by just writing this as di of s. Whenever there is this partial derivative operator with an index on it, it stands for d by dxi, it saves lot of writing, okay, you will do it like that. So, this is your gradient operator. Now, how do you do divergence? That is again very easy. You take a 4 vector, let us say ai is a 4 vector, then you define di of ai, which of course just to remind you, since we are still at early stages, di of dxi. This is the 4 divergence. What does it stand for? Let us work it out. Suppose your ai had a a0 and a, then this will work out to d of a0 by dt plus minus divergence of a. That is, your ai had components a0 and some 3 vector a, these are the components of that 4 vector. Then when you work it out, you will get d a0 by dt minus divergence of a. Now, I am sure you have seen these sort of objects before, probably in electrodynamics course, right. There is, you would have seen an expression in continuity which is d rho by dt plus divergence of j is equal to 0. Now, for the moment, I mean I have not proved it or any such thing, I mean it turns out to be true. For the moment, if I construct a vector ji or ja such that it has components rho and let us say minus j, something like this. Okay. Then I can do this and this sign will take care of itself. No, just a second. Here this is no, this is not correct. That is what was giving the product. It is plus, yeah. Okay, this is plus, so this need not have the minus sign. So if I just take rho and j, then because this is just a sum, okay, and that there is no contraction index there. So when you do this, you are going to take each one of them, each one of the components and just add them up. And if you take d rho by dt at the first component and dj by dx here, what you are going to get is essentially the left hand side of a continuity equation. So in general, whenever you have a relation that di of ai equals 0, this is usually a conservation law. Now I want to demonstrate that for you, because that is an important thing to do. Yeah. Yes. No. So let us see why we are defining it like that. How do you define divergence in 3 dimension? In 3 dimension, you would have defined it as d by dx of ax plus d by dy of ay, d by dz of az. Now I have to add to it d by dt of a0. There will be, but that change in sign will be taken care of by lowering and rising of I. If I use I on top and I at the bottom like this, I am only going to sum over them. So it is 0, 0, 1, 1, 2, 2, etc. The 0 of this will take care of that. Okay. Your intuition is right, but it is a question of definition of the contravariant and covariant component. If I have defined both of them with covariant indices, which is the way we usually think of intuitively, then it will have a flip in sign. Right now it is not. Okay. So you can define the 3 vector either with or without that minus sign, but it is just a question of convention or in a given physical context. You have to define which one is most convenient. Okay. So why is this a conservation law, or rather what is conserved? Okay. So that I want to spend some time on. Do we have a better duster than this? This probably is a whiteboard duster, is it? So no, so I need a piece of cloth or something because it's not wiping it clean. I'll try, but get a. No, is that part clear now, that why there is no minus sign? Because I first put the minus sign and corrected it. I mean, that is because I was thinking in terms of a with a flip in the sign. That is not needed. Okay. That is because of the eta ab. You see, the definition of lowering is that if I have ai, which is eta ij aj, if I look at, for example, a1, that will be 1 with a summation over j. Now we know etas are diagonal, so only the 1 1 component will contribute, and eta 1 1 is minus 1. So this will be equal to minus a1. Okay. But if I don't do that and I keep this on top, yeah, okay, thanks, then I don't have to flip this sign. Yeah, this is much better. Okay, so I want to do a little bit of analysis with that equation. To do that, we will start with this equation di of ai, which is 0, and I want to integrate this expression over a region in 4 space. So, let us spend some time on this. Again, this is nothing frightening, it is just like integrating over 3 space with one more c dt added. If it has been dx, dy, dz, you would have written it down, now you put a dt also, okay, that is what we are doing. Now, this is very analogous to what we would have done in 3 dimensions as taking divergence of A, exactly, and integrating over d3 of x, which is like dv, and you know the result there, Gauss theorem, which tells you that this is equal to integral A dot n, the normal component of the vector, through a surface which I will write as some d2 of x, 2 dimensional surface. So, this is over some 3 volume, and this is the boundary of that 3 volume. Okay. Here we are doing that integral over a 4 volume. So, the result of that will be an integral over the boundary of that 4 volume of ai ni. ai ni is just this, a dot n is just ai ni. Here it was 3 dimensional vectors, here it is 4 dimensional vectors, d3 of x. That part is fine, that is just divergence theorem in n dimension, the proof is identical to the divergence theorem. What we want to know is what is this surface and what is going on here. Okay. So, let us spend some time on that. What we need to do there is to draw a space time volume and a space time region. So, I will do it like this, this is x, this is y, this is t. I have suppressed one dimension. So, we are thinking of 2 space and 1 time dimension, okay, fine. Now, let us look at a compact region in this space. So, I will construct that region by the following way, take some region here, take some region here, and connect these 2 things up. So, I have drawn, let us say, a circle here in the xy plane. Now, this is the t is equal to constant surface. What is t is equal to constant surface? T is equal to constant is all your space. Okay. So, this region, this plane, this 2 dimensional region is actually 3 dimensional space. Now, I have this circle here which is the boundary of that 2 dimensional region. In that 2 dimensional region, I have said x square plus y square is equal to r square. In real life, it will be x square plus y square plus z square equals r square. Therefore, this circular region, 1 dimensional region, is actually a 2 dimensional surface in real space. So, this surface, and since I am taking this radius, and eventually we will take it to at a very large radius. So, this surface is the 2 dimensional surface at spatial infinity. Similarly, this is a 2 dimensional surface at spatial infinity, but this is at a later time compared to this. Okay. So, this is a good nice 4 dimensional region to integrate this expression on, and the result which you get here should be expressible as the boundary term, purely boundary term. So, what are the boundaries? So, there is a boundary on this, the cylindrical surface, and it has a normal like this, and you have to take ai ni on that boundary and calculate it. Then you have to take the value here and take this one, and then at the bottom there is another normal here, and you have to take a dot n. Okay, all of them you have to compute. Integration is in which one? Here, this one or this one? Don't. That is what this symbol tells you. What this symbol tells you is that this integration is carried out on the boundary of this 4 volume. It is just like here. Yeah, so look at it here. When you take divergence of a d3x on some region in 3 space, the integral, the surface integral in Gauss theorem is only on that surface, in the same way here. So it is integrated on these surfaces, but that surface could be all of space. It is not all of space time. You see the point, because this integral is over all of space time. All the no, what are the coordinates? Coordinates are 4 dimensional here. So all the space coordinates, okay, all the space coordinates defined on in the way I have given. I mean, this is for a very specific kind of surface. You could have said I want to take some other surface, then the result will be different. But this is the thing which we will again and again and again use, this particular surface. Okay. Now what we are going to do is to those three are always in this. When I have written it down here, I have not said what that d3x is, because I have not said what is the boundary. Now I am going to apply this theorem to this volume, okay. Then that boundary d3x on this top surface is just dx dy dz, because it is all space at t is equal to constant. That boundary at the bottom surface is also dx dy dz. The boundary on this curved thing, if I want to take it, is a weird one. There the r remains constant, radius vector r remains constant. You integrate on theta and phi, and then you integrate on t. Okay, t, theta, phi will be integrated, r will remain constant. Fortunately, you will never need to worry about it, as I will show you in a minute. We would like to do this taking this radius of this surface going to infinity. So the cylindrical surface is located at infinity, and the standard assumption in all of physics is that the things which we are working out all die down at infinity. If it is not, then we will have to take that contribution. Most of the time it works out. So your vector A is whatever it is, if it is a physically relevant quantity, it is supposed to die at infinity sufficiently fast. Therefore we will not take the contribution from that into account, and what remains is the contribution on top and the bottom, okay. So you just have to do integral t is equal to, let us say, t1 and t is equal to t2. Here it might look as though it is the origin, but that need not be. This could be t is equal to t1 and this could be t is equal to t2, okay. These are the two surfaces. You can, but in principle that gives you a bit of a problem, because what happens is that most of the time systems are evolving in time, and you are interested in knowing when the system evolves whether there are conserved quantities. In order to do that, you want to compare the systems at 2 finite intervals in time. In principle you could have taken it at infinity, but then you did not have got anything. I mean, you did not have got anything sensible, okay. So you take t is equal to t2 and the value of the integral, subtract from it t is equal to t1. It is just a to b definite integral kind of a notation. And what is needed here? The normal, but the normal here is just the 0 component. So it is a0 n0 dx dy dz. So let us look at this also a little bit more carefully. What is this surface? This surface is t is equal to constant. What is the normal to this surface? Normal to any surface we defined here. If some function is a constant, you take its derivative with respect to xi. Therefore the normal ni is di of t. What is di of t? D by dt of t, d by dx of t, and d by dy of t, d by dz of t. All the 3 of them are 0 because the independent variable, and the first one is 1. So this is going to give you 1 0 0 0, okay. So that is what I have used here to say only this matters, and that is anyway 1. Therefore you get the answer that you have this is plus or minus 1 to be precise. I will tell you what it means in a minute. So you have integral of a0 over the whole volume, okay, at t is equal to t2 minus integral t is equal to t1 of A0 d3x. What I meant by this plus or minus 1 is that depending on the direction of the normal, the sign can flip. So you always like to take this as in the time-like direction. So you would have taken it in the time-like direction like this, because the time flows upwards. On the other hand, if you think of it as a volume integral, the outward pointing normal here is downward. That is another way of interpreting this negative sign. But basically the idea is that when you do this integral, the contribution which survives is the zeroth component of the 4 vector integrated over all space.
The volume element will not be, it's not a vector.
Which volume element?
D3x over here.
Yes.
Then x vector.
Well, that is just my notation, because there are 3 of them. I mean, okay, so I mean, if I am printing it, I would put it in bold space, but you can think of it as x, yeah. Okay, so there is a naught which is integrated over the space. Now remember that physics is essentially more complicated ways of writing 0. We started with this quantity which is 0. Okay, we said that di of ai is 0. So that means this is 0, which tells you that this quantity is conserved. So this is a very general proof. Whenever you see an equation like this, di of ai is equal to 0, you can immediately write down a conserved quantity. Now if you were careful, you would have noticed that at no stage did I use the fact that ai is a 4 vector in this. Okay. So suppose ai had a I, j, k, l, m and several indices, and its derivative di with respect to one particular index vanished. Then I could have done all these and I would have had this a0, then j, k, l, m n hanging around, and I could have defined all those conserved charges. That is point number 1. Point number 2, which will come as a surprise to some of you, is that the Gauss theorem has absolutely nothing to do with vector analysis. It is taught in vector analysis, but that is just a historical accident. People say that you have we wrote down the Gauss theorem in 3 dimension here, right? It might appear that in order for this to hold, this A has to be a vector. You do not need it. This is purely a statement about indefinite and definite integrals. If you have 3 quantities, this is nothing to do with special relativity, but since nobody else will teach you, I want to spend some time, because this is a mistake which is very prevalent among people. They think that the transformation properties of the vector comes in somewhere there. It does not. Just to give you an example, suppose I take 3 components. Suppose I have a 3 component object which I will call f1, f2, f3, and assume they are not components of the vector. They do not transform as vectors when I rotate, they transform in some completely weird way, and construct the quantity df1 by dx plus df2 by dy plus df3 by dz, and then integrate it over a volume which I will take as dx, dy, dz. Okay. What you will find, just look at any one of them, take df1 by dx, and you are multiplying it by dx and dy, dz, and the moment you integrate over dx, you will get f1 integral over dy, dz at the top and at the bottom. So you take a cubical dabba and you will get just the surface integral. Nowhere I need to use the fact how f1 transforms. Okay. So this is purely a statement in calculus, it has nothing to do with vector analysis, and that holds even here. You do not have to worry about the transformation property of a naught in writing this equation down. But of course, most of the time in physics the kind of equations you will get will be covariant, and this will be a 4 vector and things will be nice, but that is just a fact of matter, but it is not necessary for the proof of this. So what we have done so far is that we have defined the 4 vectors, and we have defined objects which has upper indices or lower indices. and we have also defined a rule by which you can rise and lower indices. We did this essentially for vectors, but as you can see the same rule applies even for objects with more than one index like tensors. So, let me just write it down for completeness sake, even though it is completely apparent. So, for example, if I have an object which is Mij with both indices up, I can define from them an object with Mi, one index down object. How will I do that? I will just take eta, I want a j down, so you put a j down, then you put a k which is a dummy index, then you take Mi k and sum over k, alright. So, this is something which you can do. Similarly, you can invert it and rise it, and you can lower both of them. So, if you have a n index tensor, you can bring k of it down and n minus k up for any value of k less than n, okay. This is you can do. You can also do one more thing with tensors which has more than one index. You can do something known as contraction. What it means is you take this and then you can also go further and you take Mij and you hit it with a Kronecker delta Ji with indices up and down. This is nothing but just Mii in notation, which is like just summing over the diagonal elements of the matrix. So, it also goes under the name taking the trace, okay. So, if it is a 2 index object, it is obviously the trace of the matrix. If there are more than 2 indices, it is what is known as contraction. So, it reduces the rank by 2 because 2 of them just disappear. So, this is also an obvious thing which you can do with that. The next one which I want to introduce is what is known as an epsilon tensor. Again, since you guys have done tensor analysis, I do not have to spend too much of time. Is everyone familiar with epsilon tensors, epsilon, alpha, beta, gamma in 3D and 4D and all that? Has it been done? 3D is fine, but 4D is not. Okay, let me just go over it. It's fairly trivial. Let me just review the 3D part. And the nice way to motivate that in 3D is to look at the cross product. So, you take two vectors A and B and you define A cross B, okay. And let us look at the alpha component of this. Hereafter, I will try to be consistent and use English letters A, B, C, D, I, J, K, L for 0, 1, 2, 3 and Greek letters alpha, beta, gamma, etc. for just 1, 2, 3. Okay, I'll try as much as possible to be consistent. That's the notation I will use. So, this is 3D. So, you want to know the alpha component of this. You can write it down as epsilon alpha beta gamma A beta B gamma. Okay. Now, first of all, in 3D, since our eta ij is just 1, 1, 1, whether you have an index up or down, it does not matter. So, I do not have to worry about placement of indices. I have tried to be nice and put 2 below and 2 above, but I do not have to. I can put it wherever I want. What does this stand for? Here I define this quantity with the rule that epsilon 1, 2, 3 is 1, and if two of the it is completely antisymmetric in all the indices. So, if two of the indices are the same numerical value, it is 0, and if you interchange a pair of indices, its sign flips, okay. Then this is all which you need and you can find out every one of them. And as you can check, if I wanted the component number 2 here, I put 2 here and I immediately know that I cannot have a 2 here or here. So, it has to be 3 and 1 and 3, and that will immediately give you the curl. Now, the reason you can do this in 3 dimension, but not in higher dimensions is just combinatorics. What is happening here is the following. Suppose I want to define a completely antisymmetric object in 4 dimension. The generalization of that will be a tensor which is epsilon I, j, k, l. It will have 4 indices in them, okay. Now, the definition is exactly the same. This is equal to 1, it is defined with epsilon 0, 1, 2, 3 equals 1, and all other properties are same as that. It is completely antisymmetric in all the pair of indices. So, you flip any two index, the sign changes, and this is the definition for one of the component. Any of them are equal, if two indices are equal, it vanishes, etc. So, you can define all of them. Now, suppose you try to define a curl like this, it will not work. Suppose I take a vector ai, then I take a bj, I can hit here with a epsilon a b I j, but I will be left with two more indices there. Okay. Now, here there is this remarkable property that 3 minus 2 is 1. Okay. So, you have two of them and you take 3 indices here and 3 minus 2 is 1. So, two vectors together maps to a third vector, and in fact thinking of a cross product as a vector is a horrible thing to do. You should never think of it like that. This is like thinking of a rotation about an axis. I do not know whether that is the way you have been taught, but that should not have been. Rotation should be always thought of as rotation in a plane. Okay. So, if you take 3 dimension, a rotation in xy plane can be equivalently thought of as a rotation about z axis. But if you are in 4 dimensional space and you rotate in xy plane, is it about z axis or the 4th axis? Okay. The definition of a rotation in a plane carries over to d dimension, but the rotation around an axis is a 3 dimensional specific, again because 3 minus 2 is 1. Okay. So, this is exactly the same. The cross product should be thought of as antisymmetric tensors. For example, in 3 dimension itself, suppose I am given a alpha and a b beta, bad notation, but we will live with that. Then I can define a quantity like this. Okay. Then I can take the antisymmetric part of that. So, you take a alpha b beta minus a beta b alpha, and that is what you have here. That antisymmetric part just maps into a vector. Why does it do that? Okay, let us count the components. This will in general will have 3 by it is like a 3 by 3 matrix. So, it will have 9 components. If it is antisymmetric, the diagonal components go away. So, you have remaining 6 are paired up. So, you have 3 components, and because it has 3 components, you can map it back to another vector. Again it works only in 3 dimension, and in 4 dimension if you do the same thing, once I multiply these two, I get 16 components, and 16 components even if I antisymmetrize, which I have done, the diagonal 4 go away in that 4 by 4 matrix. I am left with 12, half of it is 6. I have 6 components, I can't map it to 4 components. Okay, that is what happens. But this is a useful object to have, and what it is good for is to construct what is known as duals. So, if you take a vector and you contract it with one index al, you get a 3 index symbol. If you take a 2 tensor and hit it, you get another 2 tensor. You take a 3 tensor and hit it, you get a vector. So, with 4 dimension you get 4 minus k, where k is the number of indices which are contracted out. So, this is, we will need it at later stages. So, I just thought this is a good time to introduce it, because we were talking about what all you can do with vector. This is another thing which you can do with the vector. Is that part all clear? Okay. Now, since we have defined the gradient, you can also do these kind of contractions and operations with gradients as well. So, the
What if I construct epsilon
I j k?
KL, AI, BJ, CK?
You can. You will get a 4 vector. Yeah, but you need 3 vectors to define a cross product then.
Yeah. So I can do that, right? Like
Absolutely,
in a
you can.
D-dimensional space, if I
D minus 1, you can do that. But with just 2 vectors, you have only a dot product in an arbitrary space. See, a dot product generalizes to arbitrary spaces, but cross product does not. But of course, if you have 3 vectors, you can construct something and you can call it. Now, I do not understand. Why do I have to lower the index? Where? In which context? So far, it is just for convenience of notation. because if I have AI on top and AI at the bottom, I can take the norm very nicely, AI. You could have worked everything out with just upper indices, because you know that there is a mapping between upper index and lower index. So, what I can do with lower index, you can do with upper index. See, it is almost like asking, why do I use a symbol like divergence of A? If you go back to Maxwell's original book on treatise on electricity and magnetism, he does not use vectors. Maxwell's equations were first written down in component form. So, it will be like dAx by dx plus dAy by dy, etc. And in that sense, you can always work everything out with contravariant indices, and you do not need covariant indices, but it makes life very, very simple. And as I told you, there is a more fundamental reason that these are completely different geometrical creatures known as one forms in a general space. Okay. I mean, just to give you a flavor, you don't have to understand the jargon here, but just to give you a flavor, let me tell you where it comes from. We will develop it more fully later on. Suppose you have a space, think of it like a surface of a sphere. Take any one point and draw your latitude and longitude. There are two curves at that point. Stick a visiting card at that point where they intersect. That visiting card is sort of tangent to that point. That is called a tangent plane. Okay. In that tangent plane, along the longitude and along the latitude, you can draw some two tiny arrows. These vectors live in that visiting card. So, these vectors live in that tangent plane. Now, you generalize it to higher dimensional spaces. At any given point, there is something called a tangent space. On the tangent space is spanned by a set of tangent vectors, and tangent vectors are vectors defined with respect to curves which are in this space. So, at every space you can define in a given space, at every point you can define a tangent vector space. Now, given the vectors which are elements of this tangent vector space, there is a particular rule by which you can define what is known as a dual space. The dual space will allow you to construct numbers out of these vectors. You give me a vector, I will give you a number, and I come with my dual space. This dual space are called the space of forms, one forms. Now, all this can be done without ever introducing the notion of length on the surface, length or a metric or this eta ab on the surface. But if this eta ab is introduced, then there is a very natural mapping between the dual spaces and the vector basis, the tangent space and its dual space. And since I do not want to do abstract mathematics, I want to start with some physical examples and do it in this way, and later on we will just abstract out the essence out of it when we go to GR at some stage. So, that is why the way I have done it, you have a very legitimate doubt that why do I ever need the covariant object. A pure mathematician will tell you that the tangent vector spaces and its dual spaces are completely different. They do not have intrinsically any connection with each other, and it is only the metric which induces a connection between these two, gives a mapping between these two, and metric spaces are special kinds of spaces, and you could have decided not to work with it. Okay. So, that is why if you want to think of a more fundamental or more abstract approach, these are different objects, but we do not need any of them. In our approach or for anything which finally has to do with physics, you only need contravariant indices or covariant indices, either one of them would do, but it is convenient to have both. Okay. Fine. Now, okay, so the question is my brief was to do 1.5 hours in each of these sessions. So, we will go on till 5:30. Is that okay? Fine, right. So, having done all these maths, now I want to get back to physics. So, I want to study the dynamics of a particle in special relativity, just as we do dynamics in classical mechanics. So, to do that, I want to first introduce the notion of action principle in classical mechanics. I am going to assume that you guys have probably done action principle, so I will do it a bit rapidly, but if you have not, I can do it in greater detail. So, how many of you are familiar with Lagrangians? And everyone is, right? You do not know. How come that? Okay, no, you have a different background, or you did not take a particular course, or you have not taken that course. Okay, fine. So, okay, so I will give a rapid overview of that, because there are again a few things which I want to introduce which might not have been done in that way in the class. So, I will do that and then we will go. So, one of the most beautiful things about physics is that every law which we know in physics can be derived from what is known as an action principle, and the simplest example is classical mechanics. So, I will start with classical mechanics. So, in classical mechanics we will define a quantity called action, which is an integral over dt of another quantity called Lagrangian, which in turn is a function of the dynamical variable's first derivative and the dynamical variable. It could also depend on time. I am not sure whether I need to keep it or not, but let me just keep it there. Okay, this is the definition, and it is integrated from some with the boundary conditions q1 t1 and q2 t2. Now, there are quite a few things which I want to say about this already. This is, I will denote it as a square bracket q of t, and if you want to be very precise, I have to denote it as this, and well, okay, q2 t2 q1 t1 with several commas. Okay, this is the most elaborate description of that. What it means is the following: it is a pure function of q1 t1 and q2 t2, and it is a functional of this q of t. Now, functional is a rule which gives you a number when you give a function. The simplest example of a functional is, for example, area under a curve. You give me a function, I will give you the area under a curve between two limits. So, this is a functional of q of t. So, depending on convenience and my mood, I can think of a either as a function of q and the endpoints and do things with it, or I can think of it as a functional of q of t and keep the endpoints fixed, and both turns out to be convenient. Now, what classical mechanics tells you is that you can vary this with respect to that functional q of t. So, what we will do is delta of this a, that will be integral dt, and when you vary this, you will get dl by dq delta q plus dl by dq dot delta q dot. There is no t which is varied here, it is only the function which is varied, dt is already there. So, this I can, okay, up to this point is straightforward. Now, we have to stare at this delta of q dot. Now, you would have been told that delta of q dot is equal to d by dt of delta q. That is the process of d by dt differentiation and the delta commute with each other and you can interchange. It is true, but you need to understand what is going on there. What do you mean when you say you are varying the action? What you mean is the following precisely. You take a function q of t, then you take another function which is q of t plus, let us say, lambda times some f of t. You choose your f of t, okay, and you think of lambda as a parameter. Then compute the action for original function and the function with this, treating lambda as a parameter, and you think of derivatives with respect to lambda. That is the way you define your variation. In that process, it is obvious that because this is the way you are looking at the variation, d by dt and delta commutes, because it is just a function and its derivative. So, this goes into integral dt dl by dq delta q, and here this is d by dt of delta q. So, you do an integration by parts, which will, and write the negative term first. So, I can even do this d by dt of dl with respect to dq dot, this whole thing into delta q, then I have plus d by dt of dl by dq dot delta q. This is what you get. Okay. You separate it into two terms. The first term you leave as it is, and in the second term you do the integral over dt, and that will give you just an endpoint contribution. This quantity evaluated at t is equal to T1 and t is equal to T2. This is the general expression you have for delta A. Now, you can do all kinds of things with it. The usual thing which is done is that you will consider the variation of the action for those variations where delta q vanishes at the endpoints. So, what you are doing here is that you are thinking of a space where you have these two endpoints fixed and you are thinking of all kinds of paths. Okay. The endpoints remain fixed and you are considering it for different paths, and if delta q is 0 and you demand that delta A should vanish, then you get your equations of motion. Okay, this is your standard equations of motion. Is that clear? I mean, this brings back the old memories. Okay, fine. Now you can do something else. You can say that I will first do that, find out that this vanishes, then I will compute the solution to that. That is, I will solve the equations of motion. I will find a trajectory which connects from here to here, which I will call the classical trajectory QC of t. This is the one for which this expression vanishes, the solution to the equation of motion, and I would like to consider A now as a function of the endpoints on the classical trajectory. So, what I am going to do now is, from the action I am going to abstract away the following object AC, which is by definition evaluated for QC of t and is treated as a function of Qt and some Q1 T1, let us say. What it means is the following: I am going to evaluate it for Q of t equal to QC of t. I am going to treat this just for convenience as Qt without the subscript. So, the upper point is what is my variable now, and this I keep fixed and it does not play any role. Okay. So, I will not even bother to write about that, but it is being treated as a function of this upper point. Then you get the result that for this delta Az, if I write down the corresponding equation, I will have delta of AC equal to dl by dq dot delta q. But these are now just end point variations. So, I can immediately get from that I defined this classical action, then I want to consider its variation when I change the endpoint q by a small amount. So, I go back to the same derivation, I have up to this point, but since I am evaluating it on the classical action, this entire term vanishes and this term survives for me and gives me this. Okay. Therefore, I get the result that d of AC with respect to dq, which is the endpoint variation, is equal to dl by dq dot. But dl by dq dot is what you would have called the canonical momentum. So, you get the relation that the variation of the classical action with respect to the endpoint variation defines for you the canonical momentum. This is actually a nice thing in the following sense: if a Lagrangian is given, usually you define your canonical momentum by sort of taking dl by dq dot. Okay. This gives you an alternate prescription. If you know the action as a function of its endpoints, then also you can define your canonical momentum without even knowing Lagrangian. Okay. I mean, in most of the cases these two are equivalent, and it is only the mathematical convenience which dictates which one you want to use, but sometimes it can be useful. For example, if you are ever going to work with a theory where an action is well defined but Lagrangian is not. You see, in order to define action principle, you only need a functional of the coordinate, I mean functional of the path. Nobody told you that it has to be of the form integral dt times L. Of course, most of the time it is an integral over a local function. How do I know that? No. You start from the other way around. You say there is a physical system whose equations of motion is obtained by extremizing a functional. Whether that functional, these are very special class of functionals. See, in general, what is a functional? Functional is a rule which will allow you to generate a real number from a function. I could have said you write the function in English alphabet, count the number of digits in it, and that in binary, and that is your real number. That is a functional. Okay, it is a completely crazy functional, but it is a functional in mathematicians language. It should have a very precise rule by which you give me a function, I should be able to generate a number. If a computer can do that, it is a functional. But these are very special kinds of functionals where you take a local object and you integrate over time. And if you are working in 4 dimensions, then you can take a local density and integrate over space and time. And those kind of functionals are what it turns out in physics we are concerned with, except some strange kinds of theories called action at distance theories, where your action can be defined without defining a Lagrangian. And in fact, if you read the history of this entire thing, most of these action functionals and the quantum aspects of action functionals, path integral formulation and all these things which was developed by Feynman, he had the motivation to use it for systems where you are given an action functional, but Lagrangian was not there. Okay, but then of course later on we use it for this thing, and just working with action, how much you can do. Okay, so but as I said, that is just a cultural remark. Most of the time you will have a Lagrangian. So this just gives you an alternate way of doing that. Okay, there is also another relation which actions satisfy, which also I want to write down, which is that partial derivative of a, this is coordinate derivative, and I do not even have to put that here, d by dt plus the Hamiltonian h, where your p is defined as dA by dq and q, this is 0. This is the Hamilton-Jacobi equation, right? I mean, you can derive it again in one step from it.
The momentum is defined this way only for the classical path or for
this for the, no, in this particular expression momentum is defined only when you take the classical path. In Hamilton-Jacobi equation, this is treated as a function of q and t, and nothing about classical path comes in. This is just an equation. You solve this to find A. Okay?
in general I can define my canonical momentum as dabba by dabba q. It is correct.
By dabba q of what? Of the action.
Yeah. Dabba
Not really, because the Hamilton-Jacobi is a very special case. So let us backtrack for a minute. I assume that has been done. See, there is something called canonical transformations, right? Now, canonical transformation, if you work with Lagrangian, the most general transformation you get, naturally get, is what is known as point transformation. That is, q goes to some other function of q. But if you work in a Hamiltonian formulation, you can start with q and p and transform to a new set of q and p. Then you ask what is the most general transformation of the system, such that the equations of motion in canonical form, p dot is equal to dh by dq and q dot is equal to that form of this thing is maintained, and that is the canonical transformation. Then you say, ha, this is very good. Suppose somebody gives me a Hamiltonian, I want to make a canonical transformation to a new system where the new Hamiltonian, let us say, identically vanishes. Then it is very beautiful, because in the new coordinate system q is a linear function of time and p is a linear function of time. I have solved the problem. The trick for doing that is what is given by Hamilton-Jacobi equation. That is, if you solve this equation, what you get for A will be the generating function for a for a canonical transformation. Therefore, even without doing that, you integrate this equation and obtain a set of constants in the integration, take the derivative of these with respect to those constants and equate it to new constants, because the q's and p's of the new thing will be constant, and that will give you the trajectory. Okay. So, when you do that, you do not talk about classical trajectories, nothing, this is just a trick, but we are going to use this trick extensively. So, I just reminded you of that. Okay. in this explicit dependent. Yes, you can do Hamilton-Jacobi equation even with explicit time dependent, but almost all the systems I am going to deal with will be closed systems. That is why even at the first line I was wondering whether I should even write time or not, but in principle you can do this even with time. Now there is something very peculiar here which I should point out to you. You find that these two equations read as h is equal to, I mean forgetting all the dependencies and all that, minus dA by dt, and P is equal to dA by dq, and if P was a vector this would have been dA by dx. Okay. Now this looks almost 4 dimensional. You take the action, take its derivative with respect to 3 coordinates and you get momentum, and you take derivative with respect to time and you get energy. And we will later on see that momentum and energy are very similar to position and time, they are components of the 4 vector. This is something which Hamilton could have written, it antedates special relativity. Okay. So this idea was very manifest even in this, and it is very naturally occurring in wave optics. And Hamilton's intuition at that time was more tuned towards wave optics, and he even went around associating a wave with particles much before quantum theory. Okay. But of course the wavelength here was all completely wrong and things like that, but it is an interesting thing to notice that this has very formal similarity to what we are doing, even though it is at the level of classical mechanics. Okay. Now what we need to do is to put this whole thing in the case of special relativity. So how do I write down a Lagrangian for a relativistic particle? So to do that, I mean that I will do in the next class, but let me start by asking how do you write down the Lagrangian for a free particle in classical mechanics. So you need a Lagrangian which is L is a function of P or let us say V and X and T in general in 3 dimension, right. Now the first thing you say is that it is a free particle, it is not acted by anything, so it cannot explicitly depend on time. Again by the same token it cannot distinguish one point in space from another point in space, so it cannot depend on X. So it has to be purely a function of V, and again it cannot distinguish between one direction from another, therefore it can only depend on V square, the magnitude of that. Okay. You can go up to this point in classical mechanics without anything else. What we have used is the homogeneity in space and time and isotropy in space. All directions are equivalent has gone in defining V square, but you cannot fix what is the functional form of this, and there you have to introduce an extra bit of physics, the physics of Galilean invariance. In classical mechanics you assume that if I have 2 different frames of reference which are going with respect to each other with uniform velocity, the transformation laws are x prime is x minus Vt and t prime is equal to t, right. Yeah. Oh yeah, that is correct. This function could be this to the power 18, then it would have been V to the power 36. I am just saying it is a function of V square, that is correct. Or in fact I am only saying it is a function of modulus of V, I mean even V square need not come, I mean you could have used square root of V square, so you would have got magnitude of V. So nothing else is assumed here. Now you have to bring in this, that the equations of motion you get for that free particle should maintain this invariance. Now in particular when you do this transformation, the new velocity V prime will be the old velocity V minus capital V, right. Now if you take any function of V square, that will now become a function of V minus capital V the whole square. So that will have one V square, another capital V square, and then there will be a dot product. Now you are in trouble because it will not maintain the same functional form as the original one. There you use the next principle. You use the fact that the Lagrangians are not really the physically relevant things in classical physics, though it can be physically relevant in quantum physics. What is physically relevant is the equation of motion. So, if I have two Lagrangians, an L2 and an L1 related by d by dt of a function which depends only on x and t, it cannot depend on velocity. If it depends only on x and t, then the equations of motion are the same. That is because when you integrate, this f will come at the end point, you are keeping endpoints fixed, so equation of motion does not change. So, you say okay, all right, I do not want invariant, I just want this Lagrangian to transform when I do this up to a total time derivative. Then you can prove that the most general function which does that is a function which is linear in V square. So, the extra terms which comes out, you assume it is linear in V square, and you show as an exercise, you try it out, that the extra terms which comes out when you do this can be written as a total time derivative. It is fairly straightforward. Therefore, the Lagrangian for a free particle in classical mechanics has to be proportional to V square, and you usually write it as half m V square, where m is defined to be the mass of the particle.
I am not clear. What is the problem with Galilean invariance over here? Why is it inconsistent with L of V square?
No, it is not inconsistent. What I mean is that if you take this and you plug in this transformation, you will not get L prime to be half m V prime square. Half m V square will not go into half m V prime square, because if
I should not expect it to go to half m V prime square, because if I am in another frame, then my velocity.
So, the Lagrangians are not invariant, neither is action. So, that can disturb you, right, because usually you expect things to be invariant, but what happens is that only equations of motion are invariant. If you are comfortable with it, it is fine. Actually, it has lot of implications in quantum theory, for example, because in quantum theory you have to look at the path integral over all. I do not know how much of quantum mechanics you have done, but there is a notional idea that you take the action and you attribute a particular phase to every path and you sum over all of them. When you do that, if I do this from another Galilean frame, then each one of them will come with a different phase. Okay. So, it does make a difference in quantum theory, but nothing drastic happens. We know that everything is fine and it is okay, but it is not a trivial statement. What on it, and you will see its implications when we do general special relativity. What I am trying to argue, and which you will see in tomorrow's lecture, is that special relativity is lot more meaningful and sensible than classical mechanics. You will find that. Okay. So, in classical mechanics, this is the best you can do. The Lagrangians will not be invariant, and you have to sort of invoke this fact that you can add a total time derivative of a function, and only the equations of motion are invariant. Okay. So, we will follow it up in tomorrow's lecture. I will stop here.
So, how do we derive it for a general particle acted upon by forces?
Okay. So, if there is a particle which is acted upon by forces, again you are in trouble in classical mechanics. We will do the same thing in special relativity, where you will see that there is a very natural way in which you can say what kind of forces can exist. The only way you can do this in classical mechanics is to say that, well, I have a function of pure velocity, I want to add to it something which will give me Newton's law kind of a structure. Okay. So, you add a u which depends only on x1 minus x2 of the particle, x1 minus x2, x3 minus x4 separation, because you want to maintain homogeneity in space. If I just move the whole thing, nothing should happen. You add such a function to that. So, it is completely ad hoc, and you will find that in special relativity all these things get into proper place, and special relativity and general relativity, and the Lagrangian is very constrained. You cannot add arbitrary potentials in special relativity. The kind of interactions which systems can have is very limited. Okay. So, we will see that. Okay. So, this is all done in a preamble to this, because when you go to a more rigorous theory, it sort of naturally selects out a subset of possibilities, while in a broader context you cannot do that, you have to invoke new assumptions in order to do that. Okay. Any questions on this part?
Even velocity dependent potentials we can solve using this theory.
Yes, you can. And so, my plan of action is that tomorrow I will introduce for a free particle the action principle in special relativity. We will work out a few things. If time permits, either tomorrow or in the next lecture, I will start doing electrodynamics in 4 vector notation. There you will see that electromagnetism falls out in a very natural way, and later on I will like to motivate and show that the general relativity also falls out in a very natural way, and other than these two you cannot have anything. So, there is a very natural sense in which you can have only two classical fields, one is electromagnetic field and the other is gravitational. It is not a rigorous mathematical proof, but it is very suggestive that this is what you can have, and that is what nature has realized.